Okay. In the last worksheet, we talked about gases that were at STP, that means standard temperature and pressure, 0 degrees Celsius, and 1 atmosphere of pressure. But here's the thing. There are many other temperatures and pressures, so you can't always just hope you just so happen to get that exact temperature and pressure. That's never going to happen. So for other situations, we use what's called the ideal gas law. And we can use the ideal gas law to predict to relate pressure, volume, the number of moles, and temperature. The reason that works is, as we mentioned before, gas molecules themselves take up very little space. The actual space that a gas takes up is the space between the molecules. So if one molecule is, say, on the left side of your room, if that was, like, say, the size of a dot, then the next molecule will be in your neighbor's house. I mean, the space between atoms and molecules of gases is humongous compared to the actual space. So we can use, in that situation, we call that an ideal gas, and we can use the ideal gas law. The ideal gas law, it looks like this: PV equals nRT. And here's when you can use it. You can use it when there's a lot of space between molecules. That means you use it if the pressure isn't insanely high and that the temperature is not insanely low. So if you're dealing with some normal level of pressure and some normal level of temperature. If it's very, very, very cold and the gas is frozen into liquid, then you can't use this. If the pressure is super high and the gas has been compressed into a super cooled liquid or a super compressed gas, you can't use this. So you can use this under normal circumstances if the pressure is low enough and the temperature is high enough. And almost all the time it's going to be. To get a temperature low enough, you would have to use like liquid nitrogen or something like that. So even if you put it in the fridge, this will still work. All right, PV equals nRT. Pressure, for us, we're going to measure that in atmospheres. V, we're going to measure that in liters. N is moles. R is a constant, specifically it's this constant here. And T is temperature. And here's the important thing about temperature is it's measured in Kelvin. To use the ideal gas law, you must use Kelvin. Here's why. You can't have negative temperature and have this work. So here's what the Kelvin scale is. Kelvin starts at absolute zero. Absolute zero is the coldest temperature theoretically possible. So 0 Kelvin is equivalent to negative 273.15 degrees Celsius. 1 Kelvin is negative 272. Oh, whoops. All right, guys, let's talk about ideal gases. An ideal gas is a gas in which the gas molecules themselves don't really contribute significantly to the amount of volume that the gas takes up. And that's most gases most of the time. For a gas, the volume of the gas is determined really by the space between the molecules, not by the volume of the molecules itself. And so when you have that situation, you can use the ideal gas law. Now you might ask yourself, well, when can you not use the ideal gas law? Well, if the temperature is so cold that you have basically created a liquid like liquid nitrogen or something, you can't use this. If the temperature is insanely high, like it's under a lot of compression, you can't use this. But if it's a normal level of pressure and a normal kind of temperature, if it's not insanely cold, like with liquid nitrogen, and it's not, this super insanely high level of pressure, you can use this just fine. Here's the equation. PV equals nRT. Get used to seeing it. You're going to see it a lot. P means pressure. For us, we're going to measure that in atmospheres. V is volume. We'll usually measure it in liters. N is the number of moles. R is this constant over here. Look at that. And T is the temperature. And we're going to talk about the temperature in a second. Now, this gas law will work for any gas. It doesn't matter what gas you're using. It just matters how many moles you have. Again, because the volume of the space between the particles is much bigger than the volume of the particles themselves. So let's take a look at the rules of temperature. Temperature for this has to be in Kelvin. And Kelvin is a special scale of temperature that we use in chemistry and physics, where 0 is absolute zero. 0 means it's the lowest temperature you can ever get. And the great thing about the Kelvin scale is you'll never get a negative number. So the coldest temperature on Earth is negative 273.15 degrees Celsius. That's not the coldest temperature on Earth. That's the coldest temperature in the universe. That's the coldest temperature you could ever have. And we call that 0 Kelvin. And then from there, Kelvin degrees are the same general size as a Celsius degree. So 1 Kelvin is just negative 272.15 degrees Celsius, etc. So you're going to be able to figure out how many degrees Kelvin you have very easily from the degrees Celsius. You might have to do a little thinking, obviously, but it's not too hard to do. So in the last worksheet, we just talked about 1 mole of gas at STP. Now, that just only works at one temperature and one pressure. It has to be with 0 degrees Celsius and 1 atmosphere. That only works in one circumstance. The ideal gas law works in most circumstances. So when you're not at STP, you can still do stuff and you still do this. What are you going to do? You're going to take the volume and pressure and whatever, temperature, and you're going to convert it to moles. When you're doing stoichiometry, you always convert everything in the universe to moles, always. And this is just one more way to convert things to moles.